Hello again, welcome back. So last time we clarified that A is a transformation of 45 degrees about by rotating the circle 45 degrees about the x-axis here. Not rotating circles, just where the point A would be if we rotated the circle. If where point O would go if we rotated the circle that far, that is point A. And B is rotating about the y-axis by 80 clockwise about the y-axis by 80 degrees, so it's a bit longer. It would be if we did it from point O, transformation B would lead us right here. So let's form transformation A, and we'll add another point on the sphere. Point O would have changed locations due to the rotation, but as I just said, instead of marking O in this new spot, we'll move it back to where it was, keep it there, and A, where it would have gone, is A. Now, we really need to clarify that we're not actually performing this transformation. We're just naming another point that exists on the sphere based on where this transformation would go. So to show what the other transformations look like, let's go back to O, and we can now perform B over here. It's nice. As well as A with a line under it, underlined A, which would be going backwards over here. So now that we've gotten this far, we might as well add transformation B underline over here from the origin O, as well as some transformation performed from our other points that we found. So let's label the points that took more than one transformation to get to by the transformations we undertook to reach them. So if we did A, transformation A, and then did transformation B, we would get point AB. This would be labeled AB. Transformation, if we did A twice, it would be labeled AA. And let's also call this label for each combination of transformations a word, so we can compare it to, well, this will eventually work like our Hyper-Webster dictionary. So due to the properties of circles and of the transformations we defined, we can actually keep adding these transformations, or letters, to the end of each word listed in the drawings forever, and we'll never reach the same point twice. Like, we can keep, if no matter how many letters we add on the end of this, once we go to AB, no matter how many more transformations we add on, we will never reach this point again. But except for a couple minor exceptions. One, and we're going to have to just quickly deal with them. One, the transformation A, then A underline would, of course, if we did A, then A underline, it would bring us back to O. That's that. So, and then also, if we do the transformation A, since it's 45 degrees, if we did the transformation A or underline A 8 times, this would be equivalent of just one full rotation of the sphere, 360 degrees. So that would bring us back to the same point. Same with B, if we did it, or underline B, if we did it 9 times in a row, we would get a 720 degrees in that case. So if since it's an 80-degree transformation. So if any word contains any of these combinations, we can just remove the combination from it. So we could say the word, see this word, A, B, underline A, B, these are 8 A's here, and then B, we could simplify this word down to just A, B, B, B. That is the same word, and this is the one we'll actually use. All the ones like this we'll just ignore. Anyways, so now we have what we need to start duplicating this sphere. This will be easier if we add some more transformations. So we'll add some letters to that drawing to make our sketch of the transformations a bit more symmetric. You can actually look at it. But that would be confusing as hell. So let's draw it a different way to better comprehend what we're looking at. So we're going to use something called a Cayley graph. Ta-da! This thing here. This will represent our infinite set of transformations and let us see as what it is, a geometric version of the Hyper-Webster. Each line segment corresponds to the path of one of the transformations we discussed earlier. We've only drawn it more symmetrically so we can, why is that showing up? So we can look at look at it in a more symmetric way. So this point O to point B. This is the same. This is the same as O to B right here, just like O to A is the same as O to A here, and so on. This just same thing, just drawn differently. So and now so at the moment this graph does not account for all of the uncountably infinite number of points in the sphere. But for now, we'll still refer to it as a sphere, as it does make the shape of a sphere that was made from an uncountably infinite number of points. So this would still, doing all these transformations, we would have a sphere made of, hollow sphere made of a bunch of dots. It wouldn't be a solid shape, but it would still look like it. Except this one, we only have, comparing it to our hyperwebster, there's only 4 letters involved instead of the alphabet's 26. So in the future, we can refer to this countably infinite set as a mini hyperwebster. That's what I'm going to call it. So now, like our hyperwebster, let's figure out how to clone this graph. To double it, let's decompose it into 5 pieces. The left green section, the right green section, the top red section, bottom red section, and the origin piece in the center. Which we can just take this point out and ignore it. We'll worry about it later. Anyways, now let's try listing off every word in one of the sections, such as this left green one right here. This isn't our first time doing this. We did it with the hyperwebster, so we know the shortcut. All the words in the left green section start with the letter A. So let's take out the first letter in each of them and put a volume A, which makes a countably infinite sphere of points. The other 3 sections don't have. We also know what to look for next, the existence of other volumes inside this one. They do exist, but there's a couple things we need to acknowledge first. What we're doing when taking out the first letter A from each transformation is we're not adding an A underline at the end of the word, we're taking out the first one. So what we're doing is we're moving A to the point origin point O and dragging all these other points with it. This isn't the same as adding another letter to the end like we did before, as we didn't really rotate the sphere, we just classified points that were on it. This time, all of the points that are on the sphere, we're rotating the whole sphere clockwise about the x-axis by 45 degrees. So here. We have all the points here, rotating them all 45 degrees this way, rotating the sphere. And they will all be dragged along with a point A, and this will be moved here. So now doing this makes point A new center point for the sphere we're constructing. Alright, next thing we need to acknowledge is a bit more obvious. Looking inside our newly placed volume A, we can now see that we have volumes A, B, and underline B. So here, this little green section here is actually, once we move this back here, this becomes equal, this little green section is actually equal to this section, like in our hyperwebster. So here, this becomes this. See, this little green section becomes this top red section up here, and we have this underline A volume left over. So, and we can tack it on to the to our little end goal here. We've successfully made a new copy by plugging this into here. We've made a copy of this Cayley graph from A and underline A, and we still have B and underline B left over. At this point, we already know how to, you can probably figure out how to make the next copy from B, where this becomes this copy, and B underline comes over here. And now, we don't even need to, our center piece is still off to the side, we don't even need a new one. And now we have 2 copies of the original Cayley graph. Now, let's get to duplicating the actual sphere. So now we're going back to when we haven't disassembled the sphere yet. We're still just naming all of the points. We've currently named a countably infinite number of points on our sphere, but that still leaves an uncountably infinite number of points that we haven't named. It's all of these ones. These ones do not cover the whole sphere. This is just a countably infinite set. Luckily, this isn't as daunting a task as it may seem. We just pick one of the points that our points here missed. And we'll use this as a new center O. And we will apply the same transformations as we did before to create another countably infinite sphere. And now we've named two countably infinite sets, or little dictionaries of Cayley graphs. And since we started at a point we couldn't reach with the first set, we also can't reach any of these points with whatever new set we've started. But we still have an uncountably infinite many points that we've missed. So let's pick a third one, and then a fourth one, and keep doing this an uncountably infinite amount of times, which allows us to say we've picked every point in the sphere. Now, we haven't disassembled the sphere yet. We're just naming all the points. We're allowed to assume an uncountably infinite amount of points. We can use it to, we're just naming things. So, and as for whether or not we can actually take each point and classify each point of this, we'll worry about whether we're allowed to do that later. But as for now, it's time to turn the sphere into two spheres. So let's think about what we just did, or at least rephrase it. We have defined the sphere as an uncountably infinite number of countably infinite sets, which are our mini hyperwebsters. We know that each of these sets is infinitely large, so that there's nothing stopping us from picking out one element from each of them. And one element is all we need to categorize every point that we can get from them through our transformations. As long as we have one point, we can we can just pick one point from each of the infinite Cayley graphs we have, and from that we can get all of these other transformations. And we know how to duplicate these. So all we have to do is organize them we can organize every A volume, every B volume, every underline A volume, and every underline B volume. We separate it into all those 5 different and the center, and we can separate them into 5 pieces by each volume, since each volume copies differently, or each uncountably infinite amount of volumes. We can still separate it into 5 volumes. And we know how to duplicate all of these, so we just essentially do it. And we've now duplicated and gotten 2 spheres from our original one. However, this was only for a spherical shell. With just a couple extra details, we can do the same thing to a solid ball, which is, a lot cooler. So how do we start constructing a solid ball? Or perhaps a better question is how conveniently we can construct a solid ball so that we can easily duplicate it. And the answer is very conveniently. We just need the uncountably infinite set that describes the rest of the ball to have one-to-one correspondence with the uncountably infinite set of points in the ball's spherical shell. To do this, we just extend a line from every point in the shell, which we have already defined. We've already defined every point in the spherical shell. And we need to extend a line from that point to the center, but not all the way to the center. We then just add one more point to fill the center, and then we're done. We don't even need to consider a separate set of lines and points. We can just define the ball as an uncountably infinite set of lines that extends to all the points that we already defined with all of our mini hyperwebsters. We can use the same exact method as we did to duplicate the sphere to the ball, but all words in our mini hyperwebsters just now refer to lines instead. Although in this method the true center of the ball is not duplicated, which leaves us a missing point in our second copy, but that's okay, as we can just fill in the hole using the same method as we did earlier when we replaced a removed point in a circle. So essentially, we're just doing the same thing as before, but referring to lines instead of points. And then we've done it. We've taken apart a ball and put it back together to two balls.